Today I'm going to talk about a lean learning resource, especially useful for purpose of teaching. So this is lean community website, leanprovercommunity.github.io. And if you go to Learn to Lean, under Lean Resources, the first kind of resources available are heads-on approaches. And you can see natural number game listed. I think many people in the audience have either played natural number game in Lean 3 or Lean 4, or if not, you have definitely heard of this. Is there anybody who has not heard of natural number game before? Okay. So most of you have. There are new games. So we have, first of all, there is now a new game server, and some of these games used to be like different places on different GitHub repositories, and now they are all unified in one place. And this is the so-called Lean game server. So if you actually click on this, you go to where the games are. There is also a game by Patrick Massot. This is the Glimpse of Lean tutorial. It's a sort of like faster paced dive, so you can also play that game if you like. But today I'm going to talk about a project that I've been working along with Jon Oyster, who's here, Marcus Ibrovius, and Alexander Bentkamp at Heinrich Heine University in Düsseldorf, not far from here. And this is basically this Robo game, which is used for purpose of undergraduate teaching at Heinrich Heine University. Marcus is running a seminar using this game, essentially, for teaching linear algebra and analysis. So I'm going to talk about this game and show you, if you have not seen Lean games, then I'm going to do a demo of this. And at the end of the talk, I will also show you how you can make your own game. So if you are, like me, convinced that making teaching or gamifying teaching helps with, speed and quality of learning, then you might like to have your own game based on, like whatever kind of mathematics you are teaching, essentially.
So where is this public? Can I?
That is public. So you need this URL in your browser.
You thought where is the link on the Lean community website?
Right.
So there is a link from the Lean community website.
Do you know?
You have the pictures that someone drew.
Somebody's too old for pretty.
That's just the
Say a
sound.
party pooper comment on the about the natural number game. I don't believe that you can recreate the natural numbers from the piano because they need second order logic to them.
So
First order piano axioms do not characterize the set of natural numbers. So maybe the wording could be changed.
For undergrads, second order logic is very, very natural. Restricting to first order logic, that's the weird stuff.
yeah.
Well, depends on the undergraduate.
So the game currently, the game that I just showed you, it's served from a server at Heinrich Heine University, and the repository where the Lean part are and where we develop the game is actually here. It's a GitHub repository, and it's this one, HHU addon/Robo. So the name of the game is Robo. It's a character in the game. So here are the contributors. So as I said, Jon is contributing, and myself, and Marcus, I guess, and Alex Bentkamp, and the other people have contributed to the game. So let me go back to the game. Here's Robo. So, yeah, I'm going to assume, because some people raised their hands that they have not heard of natural number game, so for the sake of those people, let me just give a quick overview of how the game is structured. So you have this big blue circles or disks, those are the planets. And each of them are like going to teach you some basic subject in mathematics. So for example, Logo is going to teach you basic logic, propositional logic. Implis, it's for implications, is that it's okay? Quantus, I guess, is for numbers, I'm guessing, or something.
Quantifiers.
Quantifiers, oh, sorry. Luna is for arithmetic. Then Babylon is for like finite sums. I think Spinoza is for some type theory, I guess.
Contradiction, probably.
Oh, okay, so I'm bad with it. These are for functions, Abbildungen. So the game is in German, as you have noticed already, right? Hopefully by the end of the talk you will learn some German if you don't know some German. This one, which I'm going to demo today, is for, it's a linear algebra level, essentially, where you get introduced to basic API of linear algebra in Lean. So the purpose of the game is for students not just to learn linear algebra, but become experts in using MATLAB. So we are not diverting so much from MATLAB for purpose of education. We are trying to strike a balance between learning how to do things in Lean, but also be as faithful to MATLAB as possible. And yeah, as you can see, there are some dependencies between these planets, and this dependency is generated by the dependency of tactics and definitions and theorems. So for example, if you learn something in functions, some theorem, and you want to apply that theorem in linear algebra, obviously you want to have some dependencies so that the theorems and definitions of functions becomes available for linear algebra. Here's how you can set the strictness of playing the game. So regular, if you put it at regular, you have to actually go from top to bottom. So you cannot cheat and skip and go like end up in quantus. But since I'm doing a demo, I'm just doing it for relax now. And I want to skip to, let's say, so first let me go to the developer version of it. So we have some new features in development, and it does crash sometimes from time to time, but I want to use those features for this talk. So let me skip this. Actually, let me just see if I'm in the right place.
Yeah, so for context, I think Markus Zebrovi has decided it's very fun to have like a little story. So there's like a little Robo, and it's like the story is all in German because that's how German university apparently works like. But yeah, so the images and like the story is like a little bit blah blah on top of the maths. Probably as a math student, you should probably just ignore that a little bit.
Where did you get the images from?
Well, yeah, the way funding works is that you have like a certain amount of funding just dedicated to resources, and if you cannot spend that, then that goes away. And after you spend like what you have on hard drive, eventually you spend that on other stuff. So I think that's like someone drew them.
So some professional illustrator,
Yeah,
I think so. So these are not ChatGPT generated or whatever, they're actually a person who did this. With ChatGPT. No, ChatGPT is much more, is less quality than this. This is really good. I tried actually for ChatGPT first. This is much cooler. So let me skip all. So this basically, so what you see on the left-hand side is written in German, so people who can read this, they can recognize. This is basically a narrative for the story. So in this planet, we are going to do trace in linear algebra. So this is a sort of like cartoon narrative for trace. So there is this character who, puts certain nodes on the ground, and you are supposed to go along the track or trace and pick up these nodes. And these nodes are sort of like theorems that you use to solve further levels. So I'm butchering the story. It's much nicer in German if you read it, but that basically, so this part so far is about the setting up the narrative.
Except that you selected the wrong planet, just to...
Oh, sorry. Let me go to the right planet. So this would be this one.
Yeah.
Thanks. So start. Okay, so we are at level 1 out of 11. And what you are going to learn is a standard basis for matrices. Okay, what do we have here? We have a matrix A, and that is a notation for an n by n matrix with entries in real numbers. And I and j are two just indices from 0 to n or something, maybe n minus 1. And you want to prove that if you take aij and take a scalar multiplication of this by elementary matrix eij, which actually that explains what eij is up there. So eij is defined here. It's a custom notation that we added to the game. And it defines matrix eij as the standard basis matrix eij with value 1. So this is basically a mathlib definition, and we are just using custom notation to not write this long name without the R. And here in this level, you want to prove, like, if you take this scalar and scale this matrix by that, you get this standard basis matrix whose entry at ij is aij. So this should follow simply from definition. And so suppose you're a student and you want to solve this, right? So what are you going to do? Like, what is the thing that you want to do? Well, there are some theorems here available to you. So far in the matrix tab, there's nothing that you have. So that's, all of these things are locked. You have a bunch of tactics that you have learned from all previous planets. So that's a lot of tactics. Again, some of them are locked, some of them are not accessible to you for now. For example, exact is not available.
It's harsh. You've got to apply though, so that's
You can apply, our assumption. So we want to push them to use assumption instead of exact, that's why we have locked it so far. Okay, so maybe like me, you are now a little bit like don't know what to do. So then you read all this text here. That's going to help you to have some idea of what you should do. And then there is some LaTeX stuff here that's saying basically what's going on. So for 3 by 3 matrix, we try. So this would be one example of the thing that we want to prove here. And if you read through the text and you still don't have any idea what you should do, then at the end we give you something, right? So we say maybe this E that we just defined up there, maybe you should unfold it. So let me unfold E and see how my goal changes here. So let's execute this. So my Eij got replaced by the standard basis matrix ij1. And if I go to my theorem tab, did anything change? Not so far. So I have still the same things. But maybe now I'm out of ideas, so I just try sim. Oh, that worked. And you get this now as a result, a small e basis, which says basic, okay, we can look what it says by clicking on it. It says that if I scale Eij, I get that. So that's basically the statement we proved, right? The statement we proved becomes a fact in our inventory, which we can use later.
And this fact misses a doc string, right? This is what it's missing.
Exactly. And so far we just copied that from mathlib. So we are not writing our doc string, we are not writing our definitions. But yeah, that's the doc string missing, exactly.
You can let the player fill it in. You can let the player fill in the doc string.
Yeah, that's a good idea.
Natural number game is so hard though, because you just look at it and you just write, you know, how do you document add com? You just write x add y is y and x, just like it says there. It's difficult to document.
Or how do you document this?
Yeah,
right?
exactly.
Like, this is what it is. It says what it is.
Exactly.
Okay.
Then maybe don't display missing if you have nothing to add.
Right. That's something we should do.
Or you could show the LaTeX statement there on the left. That would also be a nice thing.
Like
Save the people from having to read the weird computer code.
Yeah,
Right,
the
so
computer code's auto-generated there on top, so it's probably hard to parse.
You could literally say the same thing in later, and that would already be it. That would be it.
That would be really good. It's better than anything else. I think it's better than Word, actually.
Do we use LaTeX in comments and stuff?
I've not seen it in Math, you mean?
And if you
Yeah,
do,
yeah, yeah.
No,
if you do, does it get displayed?
I
Not
don't,
in VS Code.
yeah, I don't think VS Code knows how to do it, but like the doc.
Well, in Redux, it definitely does.
Yeah,
I think it does.
Yeah. It's just I tend to avoid it because Unicode is just you're on safer ground.
Mm-hmm. So, okay, so we are now going to level 2. So again, this is another part of the narrative. I can translate if I want, or the server crashed. So, as I said, this is a developmental setting, so it's I have to. Okay, so you're going to prove this theorem. It's called E mol of NE, basically. So what is it? It's saying, okay, now that we have defined these elementary matrices, EIJ and EKL, I want to say that this product is 0 if J is not equal to K. Right? So I have a bunch of tactics available to me, and only one theorem from previous level, that's a small E basis. Can I somehow use that, or maybe not? Well, there is no scalar multiplication here. But again, maybe we can unfold E, right? Or actually, does simp work already? Okay, simp didn't make progress. But I
What does
can.
the Feldgeschlagen mean?
Well, that means exactly this.
Command failed.
Command failed.
So you had to translate lean errors into German?
No, these are not translations of the lean errors. This is all the text of the
I see.
Exactly, yeah.
Command failed is just if you just
yeah, like
type any
object
junk.
there, right? Like
It
lean
doesn't
doesn't
like the stuff that's in the JavaScript somewhere. It would be nice to translate the lean errors. Yes.
I mean, especially if the point is getting German kids.
So we just simplified these to this guys, and now this is part of MATLib, and there must be some simple in MATLib that's that proves that.
If your exact question mark.
Well, exact is not available, right?
The exact
question mark.
It didn't do anything.
Ooh, who knows what oh, there you go. Check it out.
You
It
didn't know
worked.
that secret.
You like this more than simp? Okay, good enough for me. Let's go to the next. Okay, so if you were playing this strict and not, what is it, regular instead of relaxed, then you could not do this because exact is locked here. Okay, let's go to the next one. Control R again, reload this. Now here you are going to prove something similar, but in this case, except that the indices J and J agree here. In previous level, they were different. So again, like simp will not work perhaps.
I have a question. So in what sense is this proving anything? Because so far you've only been saying this is already done in MATLib.
Right.
So
there's nothing here, right?
What's the goal here?
The goal is, that was like, I skipped a little bit from the narrative at the beginning, but the goal is to, the boss level of this planet, the goal is to characterize trace map. So we want to prove like a trace, it's a function, it's a linear function from n by n matrices to real numbers, which kills or annihilates commutators. So f of AB is equal to f of BA. And basically trace is a scalar multiplication of such function. Or any function which kills commutators is basically trace. So that was like explained, I skipped a little bit too fast, but like if you reach to level 11 or 10, that's the final level. The idea is to use all the inventory that you create here to solve that boss level.
Okay, so you explained in the beginning that the first levels will be only calling existing lemmas.
Sure. So usually what happens in most of these planets is you need to introduce the basic API of MATLib, and this we do by a bunch of like simple questions like this. And then as we go a number of levels higher, the amount of text that appears on the left-hand side is less. Because here is more like, hand-holding students to say, you need to use this from MATLib and you need to use that. So like the usual, like maybe level 1 to 5 is more like, it's there's nothing, right? You either do sieve or exact question mark or like discover what lemma solved this, for example, and that becomes available in your inventory.
Imagine if you click there on that theorem, you will see some text rather than image same.
So mod same is exactly what you're going to prove here, and once you proved it, becomes available in your inventory.
That I understood, but let's say I'm learning this subject and I'm also learning how to do limbs, so I'm lost and all of this. I would like to know the text of what it is that I'm trying to prove.
Right.
Non-textual format, so that's what I'm asking.
So then
when you click there?
You can click on these things, and this gives you
that gives you the text.
The type of thing. So for now, the doc string or like the informal version is missing.
That's what I'm asking.
Yeah, but hopefully we will add all the doc strings to all this.
So on creating the game on each level, you have to provide your text that's displayed there. And for some reason, for ours, we decided to have like no text there ever. Like the natural number game always has like underneath like the statement in like mathematical terms, which is more reasonable in that sense. And I think that's exactly what you were looking for then.
Yeah.
Oh, I have to refresh this, I guess.
Fail.
Well, no, you typed half of a, you wrote unfold instead of unfold something.
Oh, I see. Sorry. Unfold E. That is not good.
I mean, E is not a thing. Or,
E is a thing.
oh, E is a thing.
But I think,
Let's click on that retry.
yeah, you need to retry. You need to, the problem is already there. Yeah, you need to fix the problem.
Good. And then sieve again, and then you get a level out of this. So the theorem becomes available again here as E mod of same. And you already had you get E mod of same, yes. Okay, so let me skip this. So here you're going to prove something that's going to be used heavily for the final level. And this is the fact that any matrix can be generated as the sum of these elementary matrices. And already here, like, things get a little bit more difficult. So again, I guess we want to use some theorem in MATLib. And so here we already like introduced something from MATLib, that is something in yellow. So this is, and if you hover around it, it says like any X matrix X is sum of like standard basis matrices. Except that here, our thing is not really standard basis matrices, it's some scalar multiplication going on here. So we want to sort of simplify that scalar multiplication to get standard basis matrices, and this was the first level we played. This was this guy. So maybe we want to write simp of that. I wonder if this will work. Okay, so your goal became something that this guy should take care of. So can we right now apply that lemma? So let me copy this, it's a long name, and put it here. Okay, level complete. Good. So I guess this name should suggest that we want to express 1 as some of the diagonal matrices, diagonal basis matrices. So yeah, we want to say sum of EII's is 1. So let's try simp. That will probably not work. Unfold E maybe. Now we have some statement here. What can I do now?
Maybe Xed.
Xed. That's a good idea because this is a matrix now, and this is a matrix, and matrices in Lean, Patrick knows more than students at this point, but matrices are encoded in MATLib as functions essentially. So there are 2 argument functions. So I can do X on that definitely. But is this what we are saying to students? We are saying that they should use the matrix EQ sum E basis. So I guess we want to expand this one to sum of E bases. So maybe then unfold here was not a good idea.
Turns out this, because once you prove that the elements of the sum are the same after expanding in terms of the bases, that's X.
Okay, sim failed. Can we guess why this is the case? Maximum recursion depth has been reached. So the problem with this is you can do this, but you can do it to 1 and you can do it to E as well, I guess.
No, the problem is that you can do it to the result of doing it. That's the problem.
Oh, yes, yes. So you expand 1 to sum of, and then you can sim that.
Standard basis matrices also, you can use it.
That's right. So
Just do rewrite.
we can do rewrite.
Then space 1, matrix X sum basis.
So if we look at the type of this sum E basis, you can see that here A is an explicit argument. That means you have to provide A.
This one has comments.
This one has comments. That's nice. So definitely we have not developed things as uniformly. This is still work in progress. So we have to give A, or in this case 1, as argument to this lemma. And 1 in this case is just identity matrix. Okay, so what we did is like we expanded this one and rewrote it by this double sum. And here you are trying to prove one sum is equal to another sum. And here you can see that once I did this step, some hint appeared here. And that hint is basically saying you can either use conger or you can use ext to go further. Because I think like at this stage it's hard for students who have not seen sums before to figure, well, actually we have a planet for sums, but this is a sort of reminder that these tactics are useful to like make. So this is essentially sum over a function, and this is sum over a function. And you want to prove those underlying functions are equal. So if I do conger, then I get that this function that sends E to EII, it's the same as this function.
What is this implication in the middle?
So that's supposed to be a function that's a matrix function. But I wonder why we don't have this maps2 thingy here. So
There's an option that you need to set.
okay,
Then that's probably something we didn't do yet.
okay, we should do that. Okay, so now you are trying to prove two functions are equal, and here's where this extensionality principle comes in. So remember, so here's a function, right? But the result of this is also a function because EII is now a matrix, which is a function. So you can do xi r s or something. And so now here this becomes a scalar, and you want to prove that this is scalar.
Yeah, I think you would X too many things, right? You
No,
just
no.
did X of I.
So I think in the new mathlib it's fixed that this here would be displayed as sum, but somehow, like, it just doesn't display this as a sum.
Well, it's a sum applied to two things.
Yes. And so now, I mean, in the context, what do you have in context? You have IRS, and you are summing over all j's. And here you want to have hopefully a lemma that says, you know, like, if j is equal to I, then one of ij is just one. E of ij becomes EII, and you have RS, so this becomes IIRS. So, but now you're splitting cases, right? By saying, is j is equal to I or not? And this is where this lemma is used for. Here, what you're doing is like you're taking a sum and you're saying that the index of that sum either is equal to I, which means it belongs to the singleton, or not. So if you rewrite along that lemma,
Excuse me, I wasn't, I guess, fully paying attention. So this part of the discussion just appeared after the ext tactic, right?
right? So it's, yeah. So if I do this, hopefully, I get something useful. Right, so now I have this singleton I. So before I was taking the sum over fin n. I now take my sum over singleton I. So if I do simp, does that help? Okay, it did solve my goal because Lin knows how to take sums over singleton essentially, except that I needed to, have a condition for taking that sum, and that is that when x is not in the singleton, this has to be 0, because this is exactly what this lemma is saying. It's saying wherever the sum is 0, we just don't take it. Wherever it's non-zero, we add it. Was there a question? Okay, so now you have to prove this, and maybe, okay, so this is an implication. So you want to say for every x and for every proof of this, this is true. So you need to do some bunch of intro here. X, maybe hx, and maybe one more, hxi. So I have like I added as a some number below n. I know that x is in the universal subset, which is basically the whole thing fin n, and I know that x is not I, and I want to prove that this guy, this scalar multiplication is 0. Well, I somehow need to translate this to say that x is not equal to I. And when that happens, this guy becomes 0. So if I just do simp, that doesn't do anything for me. I mean, it does something. It sort of simplifies this scalar multiplication to or, well, I can follow up from there, or I could have been a good student and followed the hint. And saying that, not belonging to singleton is the same thing as not being equal to x. So.
What's this background? Okay.
Yeah, sorry. I was hovering over this.
Oh, is the z order on the covers messed up?
The z order's messed up.
Yes.
Yeah.
Okay.
So for context, that's also why everything's breaking, because that thing I just started fixing yesterday to go to new lean version, and that's not finished. But I think it's halfway workable on this.
So maybe I backtrack one step. Instead of doing simp, I actually follow the hints here. I mean, you could have proved that either way. So I can say have I not equal to x. And that will probably generate a new goal for me, saying that you have to prove this from what you have here. But this goal should be something that simp can do.
You simp hxi, you mean?
But yes, I need to use this fact hxi, exactly. Otherwise, how would it do? Okay, maybe I go back here and do simp hxi here.
Simpa using hxi.
Simp A?
Yeah.
Like simple?
Yeah, using
hxi.
We'll see
Let's
whether
try
this
that.
one is blocked.
Oh, and you got it wrong anyway. Look at it, check it out.
Yeah.
Let's try.
It's the ordering is
Simp.
That's true.
Simp first.
Make egg.
Simp at
No,
hx.
SYMN first.
I'm going to with Mario. So
simp at hxi.
Yeah.
And then simp hxi.
thank you.
No, that will do the same thing that it would do.
Well, dot sim maybe.
Yeah, that's.
Yeah, but okay, you could have done it. But why don't you want
It
to
looks
use
like
this?
Düsseldorf has pretty impressive
It does say something sim.
undergrads if they can do what a whole room of lean experts cannot.
No, but we are not reading the hints. The hints are there. It says you should use sim here.
Ah, I didn't even see that.
You need eye tracking.
It doesn't work.
So,
No, I mean, you have to apply any dot sim.
so can I do sim first?
You should skim this and then use sim.
Sim this?
No, sim, that's
yes.
enter, and then.
You've already keep it
Oh,
not equal.
yeah,
you
start
simp and
with
screw,
the
yeah.
first simp. You need to move back.
Back one.
Yeah.
Okay.
Because
This one
this is when you should.
Sim.
Just sim, just normal sim.
No,
Sim.
Sim. That is what's written here. You're right. So, oh yeah, sim is a tactic. I keep forgetting sim is also a tactic. So it should switch this, right?
Yeah.
Make it like x is not equal to I. Okay. Yes, good. And now I can do sim at hxi.
Sim.
Simp using H.
Simp using.
Oh, no, there's no simp.
Well, now simp of HXI should work.
Okay, now
No,
that
exact HXI should
that is what.
Exact doesn't.
I hope the Fermat's last student is super
It's much easier. It's much easier than this.
So we solved one goal, and then the remaining goal is like this when the.
We cheated.
So I'm going to next step. Sorry. I mean that's the fun of playing a relaxed version. You can always go. Okay, so that was like maybe the very basic API and stuff solving, and here's maybe the more serious levels start after 6. And so if you want to prove like we can characterize trace by functions which kill commutators, then maybe we need to prove some lemmas before doing that. So for example, if I have this hypothesis, then I want to prove like f of all diagonal elementary matrices are the same. Okay, so my goal is universal. Students by this time have learned how to prove universal quantifiers. You need to intro I. So this is not something we put in hints because by this level they should know logic. And here I have to use this to get this, right? So I mean that is the more creative step, and we have put some hints, right? And if that hint is not enough, you can ask for even more. And then that tells you exactly what you should do. So here, for example, one way to do this is using this trans tactic, which is mentioned over there. But obviously another way to do this is actually using this lemma, specializing to EIJ and EJI. So you can specialize your goal, H1. Specialize. I always put H1 to EIJ and EJI. And what specialize does is basically puts EIJ in here and EJI for me. Okay. Tactic specialize is not available in this game. Great. We will make it available, hopefully. Or you could make it have. You can also write a have statement to not overwrite H1. Right now we are overwriting H1. So anyhow. So this guy, EIJ, EJI, if you remember our theorem, so if I click on this tab, we had this theorem which said mal same, which said if this index j agrees with this index j, then this product should be EII. So I'm going to use this, and you can always look at this, what it says, right? It says like if j is j, then this becomes EIK, and I want to apply that lemma. And because this lemma is an equality, the tactic that you should use is either rewrite or sim. So I can copy this guy and put it in here.
H1.
Thank you. Okay, good. So it did two things at the same time. It simplified right-hand side and left-hand side at the same time, because the lemma applied to both. And obviously, this is exactly the statement of H1, so you can write assumption. Okay, good. So, Control R. So this is saying if they are off diagonal, then they are 0. The previous one said if they are on diagonal, they are equal to each other, and this one is saying off diagonal, they are 0. the proof is going to be similar, except that this time you want to use a different theorem, mod of none not equal. So I'm going to skip this. So this is the more interesting one that's going to be useful for us. EQ sum apply direct E basis. It's saying, so we had this statement that any matrix A could be written as sum of AII, EII. So if we ignore F, we already proved this. And the name for that was, I think it was matrix EQ sum E basis. Right. Here we are adding a linear map F. So what should I do? Well, there's some hint here. It's saying whenever you have a linear map, you can distribute it over sums. And once you distribute it over sums, you get something like this. And then you can apply that lemma here. So I'm going also to skip this, but feel free to try later. But I think like the combination of LaTeX and the inventory should be helpful to maneuver over this. Okay, so here's another lemma that will be useful, and this is saying, for every I, f of EII is 1. I'm also going to skip this for now, and this will give the name 1 on direct E basis. So this is the boss level, and the concept of the boss level is there will be no new theorem or new tactics and no new hint available to you. You should use all the things that you have learned in previous levels to solve this. So for most part on the left-hand side, it's just a narrative really, and what this plan is about, and there's not much more hint. So here what you have is, you have a linear map F from a space of n by n matrices to R. You know that F kills commutators, and you know that F of identity matrix is n. And you want to show that F is exactly trace. So maybe a comment here is, usually for boss levels, we don't want our theorem to be in mathlib, because then you could just write simp. So we want to have something that uses a lot of mathlib, but it's not in mathlib, and it's fundamental enough that we should care about that theorem. So in this case, it's nice to characterize trace. And we are looking for, if you have such questions in mind, like if you have some nice, not big project questions, but something that can be fit into like 10 or 12 or 13 levels, then please write to us or talk to me or talk to Jon. We like those questions.
So you mean that if at the end of your talk we go and add this into mathlib, then you're...
And then you can write simp here.
Because no, I guess we would never do that with the matrices. It would be with endomorphisms of dimensional vector space.
Exactly. So it's concrete enough. And also it's maybe a concrete version of a generalized theorem, but that cannot be just applied or simped, because it's a little bit different than that. That can be candidate as well. Okay, anyway.
But what you really need is a way of castrating lean, right?
Yeah.
Well, I mean, there are already several ways of castrating, like not being able to use special tactics. I'm guessing you also can't use unknown theorems, or like.
What do you mean by unknown theorems?
Well, I don't know. If you just pick a random theorem in
If you just add one, then it will say like this theorem is not available in the game.
Yeah.
Like that.
So,
Or you can plug simp, but we don't want to do that. We want to use as much mathlib as possible.
right, so if someone proves the characterization of trace,
Yeah.
you could say that this theorem is not allowed to be
Okay.
used, right?
Yeah, if it's not unlocked or not existing in the inventory, then it will not be allowed.
Okay.
And for simp, I did think about just intersecting the simp set with like the set that's available here, but I didn't do that yet. But that might be a way to further like make simp weaker, just saying like use this custom simp set that has only very few lemmas in there.
Anyway, I don't want to bore you with this, so if you are already by this time interested in the game, this is something you can do now. Go to Atom HHU and then try to solve this. Basically, all you need is now, you should use these theorems and nothing more. And yeah, the tactics that is available here. Okay.
What do the colors or color densities mean?
The brightest means this one has been used exactly in the previous level.
Ah, okay.
The lighter version means in this planet being used. The other ones, so why is mod of NE not purple? Like this one, why is this not purple? Because we actually proved this in level 2.
But not
So
the
the color's just been added very, very recently, but
Okay.
all the purple ones are the ones that are actual levels in this planet. The dark one being the level just previous, and all the yellow ones are the ones that are added in this level as like new statements from MathLib. So it gives you some hints to them because it's quite a lot of theorems available at some
Right.
point.
And also like,
What is the purpose of displaying the logged stuff? Because it's cluttering the interface a bit. Yeah, why do you want this?
I agree, like we don't need this. I mean, why?
I mean, this is not that unusual from like games, right?
Exactly, that's a design choice on like seeing like how much progress you make of like being stuff locked or having. I think originally I had them all like just hidden, and then
But trace as small, I mean, we don't need this right here.
I think it's in the next level. So
Okay, I see.
yeah, I think originally I had it to just have those 4 hidden, and then at some point it was decided to actually show the locked stuff to give you some feeling of making progress.
Sounds good. Yeah, and then like if you think like something in, I don't know, surjective can be useful for this, I doubt it, but if you think something you played in the level surjective functions or whatever can be useful here, you can always click on this and use one of those theorems. But okay, anyway. So at this point I want to just, if there's no questions about this linear algebra game, I want to quickly show you how you can make your own game. So if we go back to Lean Resources, and we go to Lean Game Server, and we scroll down past the games, there is this game, a skeleton GitHub repository, which tells you how to create a game. So this is the GitHub repo, and you click on creating a new game. And basically here is like the guide that you should do. So the first thing is like to clone this template and run lake update lake build in your repository. The rest of it is useful for like creating levels, creating planets, and serving locally. But let me just show you something that so I have done these 2 first steps, and I can show you quickly how it looks like. So here's game skeleton, and let me close this editors here. And this is demo world, so these are like the levels of your game. So these correspond to planets. So we have a bunch of planets, injective, surjective, Botswana. So they will be placed in these levels. Then, so this is a planet now. It's called demo world. And in that, there's only one level. And it proves this statement. Let me make this a bit bigger. And here, every planet has, so imports all that game metadata, which has custom tactics, definitions, lots of other things. Then it has that string that says this belongs to demo world. It's the first level, and some introduction for the text, and this appears on the left-hand side of your level. And here's the statement that you want to prove. The hints that you used to see come here. So for example, if I execute this rewrite age, this is the hint that immediately appears after that. And then there are branches which are like for alternative, so you can have different kind of proofs, and if you go to that branch, you also want to see the hints for that branch. And yeah, I mean, there is more that can be talked, but I want to stop here, and if there are questions, and Jon can answer the questions.